Hello everyone. Today we're going to analyze the circuit that is known as a high-pass filter. This video will show how basic theory, some math, and testing are used to help engineers approach circuit design. Now, we could build the circuit and conduct our testing with multimeters, oscilloscopes, and spectrum analyzers, and then refine our design, test again, and continue like this until our design objectives were met. However, such an approach is quite expensive, and most professional designs today are begun using a series of simulation tools. And so to help us with the analysis here, we're going to use a simulation tool known as Multisim, created by National Instruments. So we have a simple circuit consisting of three elements: a voltage source, a capacitor, and a resistor, all in series. And we're going to focus today on the voltage drop across the resistor, R1. When we do this, the circuit is known as a high-pass filter. High-pass means that when the circuit is sent a series of voltages whose amplitudes are changing, the voltages with higher frequencies appear across the resistor, and voltages with lower frequencies are suppressed. That is, higher frequencies are said to pass, and low frequencies are blocked. This is the essence of the term filter. Only desired components are allowed to appear or pass through the circuit. We could have chosen to look at the voltage across the capacitor as our output, and then we would have another circuit called a low-pass filter. Low frequency voltages would appear across the capacitor, and high frequency voltages would be suppressed. But that's a story for another day. Now, when thinking about this circuit, the first thing that must be recognized is that the voltage source, which appears on the left-hand side of the circuit, is producing or injecting sinusoidal voltages. Therefore, the output across any element, including the resistor R1, which is our focus today, will also be sinusoidal. Now, sinusoidal voltages are used so often that novice engineers often think that voltages are always sinusoidal. Not so. Sometimes triangle voltages are used, and sometimes square pulses are used, especially in digital circuit designs. Today we're using sinusoidal voltages. The formula in blue font at the bottom of the slide shows the mathematical form of the voltages being considered in this demonstration. Since the voltages are sinusoidal, we'll be calculating and measuring three different properties of this formula, and these are amplitudes, frequencies, and phase angles. Now, the amplitude is typically written as the capital letter A, but I substituted V0 to reinforce the concept that we are dealing with voltages. Frequency is captured in the omega term, and the phase angle, of course, is the theta term. We'll go into all these elements in much more detail. Now, when looking at this circuit, one should immediately think voltage divider. It is the first circuit one learns in a circuit theory course, and it is an extremely useful circuit when analyzing more advanced designs. Using our voltage divider rule, we know that the voltage across the resistor R1 is R1 over some equivalent impedance term times the value of the input or source voltage, which is given here as V1. Impedance is the term we use to describe resistance when dealing with voltages that change over time. That is, when dealing with AC and not DC situations. If the capacitor were replaced by a resistor, let's call it RC1, then the equivalent impedance term would simply be the sum of the resistors RC1 plus R1. To get the voltage across the resistor, R1, we simply replace the impedance of the capacitor for the RC1 term in our voltage divider rule, and we get equation 2. Now, I'm not deriving it here, but the impedance of the capacitor, also known by the term reactance, is given by the equation 1 over j omega c, where j is the complex number, omega is frequency, actually angular frequency in radians per second, and c is the capacitance in farads. When we combine the capacitor's impedance into our voltage divider formula, we get equation 3. This equation contains everything we need to understand the voltages that appear across the resistor R1. Our goal today will be to get some intuition for this equation physically and mathematically. We're going to start our analysis by looking at the magnitude of the voltages across the resistor. By thinking about the capacitor's physical behavior at two limiting cases, that is when the frequency is 0 and when the frequency is large or approaching infinity, we can begin to develop some intuition about how the circuit will behave. When the frequency term is 0, the voltage source is essentially a battery, which we've seen in our DC analysis of circuits. In a DC circuit, the capacitor would charge until it was at the same voltage as our source voltage, and at that point the current would stop. The charged capacitor would then act like an open circuit. Since there is no circuit flow when the capacitor is charged, the voltage drop across the resistor R1 would then be 0. So when the frequency is 0, the voltage drop is R1. The voltage drop across R1 is also 0 after some short interval when the capacitor is charged. Now, when the frequency increases, the capacitor behaves differently. As the frequency increases, the capacitor's impedance starts to decrease. To understand this, it is best to rely on the mathematical formula provided in the upper right-hand side of the slide. As omega, or frequency f, gets larger, xc, or the capacitor's impedance, gets smaller. As f approaches infinity, xc approaches 0. At that point, the capacitor simply looks like a wire, and we call it a short, and all currents of all frequencies pass through. So, as we increase our frequency, we expect the voltage across the resistor R1 to start from 0 in DC conditions and increase to the source voltage when the capacitor effectively shorts out and behaves like a simple wire. We've captured this behavior in the blue curve on the right-hand side of the slide. At this point, we don't know the detailed behavior of the circuit in the intermediate frequencies, but we do know the starting point of Vout is 0, and the end point of Vout is V1, the voltage of the source. That is, we don't know how fast the slope of the voltage curve changes, and this will depend on the actual terms of R and C used. And finally, we do know Vout will approach V1 asymptotically because we never get to an infinite frequency. Now, we'll observe all this behavior later when we probe our circuit with some test instruments. Now, we can develop a similar intuition or feel for the phase response across the resistor by relying on the concept of phasors. Now, all of the phase data is contained in the boxed equation 3 on the right-hand side of the slide. Vout is a complex number, and we're showing Vout in Cartesian form. The Cartesian form of complex numbers are useful, that is, computationally fast, when adding voltages. For example, when voltages in series are added. When dividing or multiplying voltages, phasors, or the polar form of complex numbers, are most convenient. The phasor is a vector in the complex plane. This vector has both magnitude and phase, and these are exactly the quantities we want to derive. To refresh our memory of phasor math, I've reproduced the formulas for the product and quotient of two phasors in blue at the bottom of the slide. When multiplied, the magnitude of the product is simply the product of the magnitudes. The phase angles, however, add. When dividing, the magnitudes divide as normal, but the phase of the quotient is given as the difference between the numerator and denominator. When dividing, phase angles subtract. If this is a new concept, then I suggest you consult the text on phasor arithmetic. I particularly like Kreyszig's Advanced Engineering Mathematics for its handling of this subject. For most topics, my go-to for advanced math is Riley and Hobson's Mathematical Methods for Physics and Engineering. Okay, so let's break down equation 3 by first looking at the denominator. And we're going to mix both Cartesian forms and phasor forms of the complex number, depending on which notation is computationally easier. When adding or subtracting, we'll use Cartesian forms, and when multiplying or dividing, we'll use phasor, or the polar form of complex numbers. Now, the denominator is simply the sum of the resistance R1 and the impedance of the capacitor, which we've denoted here as x sub c. R1 is the orange vector, and x sub c is the red vector. R1 is simply a real number, and so it sits on the real axis and has a phase angle of 0 degrees. The xc term is a purely imaginary number with a magnitude of 1 over omega times c. The phase angle is captured by the negative j term, which is equivalent to 90 degrees. Now, let's back up a second and explain why complex numbers appear in the first place. First, j is used in circuit engineering because I, little I, typically represents current, so a new variable was found. Furthermore, complex notation appears because sinusoidal voltages do not combine mathematically like real numbers. Mathematically, they combine like vectors, and this is why complex numbers are used. The way to think about j, then, is simply as a rotation. Multiplication by the j term should be thought of as a rotation by 90 degrees clockwise. For example, 5 times j is a vector that sits on the imaginary axis, which is rotated clockwise by 90 degrees from the real axis. The product j times j is simply 2 clockwise rotations by 90 degrees, or 180 degrees in total. So, for example, 5 times j is then equivalent to negative 5. And j cubed would be 390 degrees clockwise rotations for a phase angle of 270 degrees. And this continues for each additional j term. A negative j term rotates by negative 90 degrees. 1 over j, as we showed in the last slide, is the same as minus j, or negative j, and therefore should be thought of as a vector rotation by negative 90 degrees. So xc is a vector that sits on the imaginary axis and points vertically downwards. The denominator is the sum of the orange and red vectors, and it has a negative angle, which we call theta sub eq for theta equivalent. The actual numerical value of this angle will be worked out later. Right now, we just want to show or know the sign of the angle, which happens to be negative. The quotient vector, shown in green, is the result of the division of a real number, whose phase angle is 0 degrees, the orange vector, and some additional phasor, the black vector, whose phase angle is negative theta equivalent. Now, according to the rules of phasor division, the phase angle of the green vector is 0 minus negative theta equivalent, which equals positive theta equivalent. So we now know the phase of V out. Since V1 is a real number and has 0 degree phase angle, its product in the equation will not change the phase angle overall. That is, the phase of V out, as captured by the green vector, is positive theta equivalent. The real insight is this: the voltage across the resistor will always lead the voltage of the source by some positive angle. This angle changes as the frequency of the voltage source changes, but it will always lead the input or source voltage. We'll confirm this when we look at our oscilloscope data in the next slide.